Okay, before we get started, yeah, come on in. We just get started, didn't miss anything. Okay, so the first thing we want to go over is what exactly is thermodynamics and what kind of questions are being able, or thermodynamics can help us answer. So that's a general overview here. If you think about chemistry as a field that you have either microscopic or in specific how molecules and atoms interact with each other, so that's a more macroscopic part or dynamic of the chemistry work. And on the left-hand side, we have, that's reverse. On the right-hand side, we have thermodynamic, which is the more macroscopic. Right, so macroscopic, you're dealing with things you can see and touch, right? You can see an object doing work or a gas expanding or compression. Now, in between, we have statistics mechanics that links thermodynamic and quantum mechanics, but we won't spend too much time on it. We will likely focusing on the macroscopic end of the spectrum. We will be mentioning a little bit on the atomic nature and what exactly does some of the thermodynamic means, but we'll focus on the macroscopic spectrum. And in detail, eventually, the one question we want to answer is how do we use thermodynamic to predict the movement of equilibrium, whether it's an equilibrium between different phases or equilibrium for a chemistry reaction. There are other topics that are relevant. You can also see that in your textbook, like kinetics of a reaction or how fast a reaction takes place. So thermodynamics will not give you that information. Right? Thermodynamics only tells you, hey, you have one substance here, you have a product here, or you have a different substance here, and how well these two substances end up to an equilibrium state at the end. It doesn't care how fast that transformation takes place. Or if we want to use our textbook definition, we have thermodynamics. It's a study of heat, work, energy, and the change they produce in the state of systems. So obviously in here, we have a lot of terms that we need to be defined, right? What is heat? What is work? What are different forms of energy? What does it mean by different state of the system? And what exactly is a system? And what does thermodynamic equilibrium mean? So all the things in thermodynamics is something like you read the sentence, you'll be like, okay, I get it. But then if we ask you, what is the definition of each term in that statement, that becomes a little bit more challenging. So the first thing we want to do here is to define some of the terms here, just to make sure we have the same vocabulary to talk about in thermodynamics. Okay, so moving on to our terms in thermodynamics. So that's your chapter 1.2 in your textbook. So in this section, we will have lots of definitions. First of all, we just mentioned system. So system and surrounding is normally a pair-wise concept that people talk about. For example, if we're using like this bottle as a system, right? Whatever inside, we call it system, and whatever outside, we call it surroundings. So basically, that's the full definition is the macroscopic part of the universe, which is something in the bottle that's being under study. And the surrounding is everything else in that universe. That's the first pair of definition. And then we have several descriptors for a system. Now, a system can either be open, means you can transfer matter and energy in and out from that system, or it can be closed, where you cannot transfer matter in and out, but you can transfer energy. Or it can be isolated, means no matter transfer and no heat transfer. But isolated, technically speaking, that's only theoretically available. In reality, you don't have something that's perfect isolated. So now imagine this bottle again, right? What is a system here? like imagining the side of it is preventing the liquid inside the box to get out, but it doesn't prevent it. It doesn't prevent the liquid in the box to be heated up because I'm holding it with my hands, right? So what is the system? Yeah, yeah, right. But if I open it up, now it's touching the air, so the alcohol in there can evaporate. So naturally, now it becomes a open system, right? So, I mean, these things sound straightforward, but it's one of those things like the closed system is a little bit counterintuitive. You need to keep in mind that in closed system, you have heat transfer in and out of that system. And just, yeah, a little bit more example here, like, is our planet Earth a open, closed, or isolated system? Yes, I mean, it's big, right? But it's still an open system. You can have free material change and also heat change with the rest of the universe. But now if we're considering a box of milk, right? Imagine your milk cannot go outside the box, and it's thermally conducting, so that milk in there will give you a closed system. And occasionally, or most of the time, we will also highlight it's non-isolated. All right, so that's the first few definitions. We define what a system means, what surrounding means. And we have 3 different types of system to be considered: open, closed, and isolated. Now, in this case, we are talking about this box or the wall that's separating your system from the surrounding. There are several descriptions we make on this box. For example, we call it rigid, impermeable, and thermally conducting. Right? If it's the same idea here. Rigid means like you don't have like expansion and compression of that wall. Impermeable means the material cannot go in and out. And thermally conducting means heat can go in and out. So these are the criteria for walls. We have different kind of walls we want to mention. So again, a wall is just something that separates 2 systems or system from its surrounding. Now you can have rigid and non-rigid wall. So a rigid wall means it's something hard, it doesn't move. And a non-rigid wall you can imagine to be something soft, and you can sort of change the shape, and also it can compress or it can expand. So it's movable or not, that's rigid or non-rigid. Next up, we have permeable and impermeable. So permeable and impermeable tells you whether or not our wall allows matter to be transferred between different sides of the wall. Okay. And then the third one is something new, hopefully, for you. It's called adiabatic and non-adiabatic. So these 2 terms we will use extensively in thermodynamics. So adiabatic wall means that wall does not conduct heat. A non-adiabatic wall will be thermally conducting. Now your textbook has the longer version of the definition, but these are the gesture I hope you can grasp. So adiabatic, non-adiabatic tells you about whether or not heat transfer is allowed. Permeable, impermeable, that's a set, tell you whether or not material transfer is allowed. Rigid, non-rigid tells you whether that wall can move or not. Okay, that's different kind of walls. I know it's a lot of definition, but we have a little bit more to go. Now we're talking about equilibrium. So when we're talking about equilibrium of a non-isolated system, means that system is somehow interacting with the surroundings. You have 2 different criteria that must be met. The first one is called the system's macroscopic properties must remain constant at any time. Or what does that mean? Is, for example, if we're looking at something in there, right, again, the macroscopic properties like pressure, volume, temperature, if I just let it sit there, like it's gonna stay. So that means whatever inside and outside between the system and the surrounding is in equilibrium with each other. That's one of the criteria. And the second criteria is that removal of the system from contact from its surrounding causes no change in the properties of the system. I know it's a long definition, so effectively what that means is now imagine these walls just all of a sudden disappeared. Now, if we don't consider gravitational force, which means your liquid will drop, like if we ignore that gravitational force, they will pretty much remain the same pressure, volume, and temperature, and also other somewhat macroscopic properties. Okay, so with that in hand, we have different types of equilibrium. I promise you this is the end of it. We're almost there. We have different types of equilibrium. Now, depends on how many of them are being checked. If all of them are being checked, we say we have thermodynamic equilibrium. Now, in here, we have three different types of equilibrium we will be talking about. The first one being mechanical equilibrium. So mechanical equilibrium just tells you the force or macroscopic force and movement are being balanced, or effectively what it says is the system undergoes no acceleration. Right. The second one being material equilibrium. So material equilibrium, judging by its name, it's talking about the material are in equilibrium with each other. It means like we're not having any chemical reaction going on. We do not have any transfer of matter. Or the other way to put it more precisely, when we say no chemical reaction taking place or no transfer of matter, what we're saying is, for example, if we have 2 cups of water here, they're at different concentration, you mix it and eventually you'll reach the same concentration. What we're saying is that at that equilibrium point, it's not like nothing is going on. Rather, only things of very small steps or infinitesimal steps can take place. We'll have a more precise definition of equilibrium when we actually get to the equilibrium chapter. So for now, just keep in mind when we talk about mechanical, we're talking about the system doesn't have acceleration. There's no PV work. When we talk about material, it's more or less the composition of that system doesn't change chemically or physically. And we have thermal equilibrium. So the thermal equilibrium definition is something that we're going to use the term we just defined. So imagine now you add a non-adiabatic wall. And it will cause no change. All right, so what that mean? Like, for example, if you have a box somehow, and everything inside that box have the same temperature, let's say T1. And now all of a sudden, we add a non-adiabatic wall. And the temperature will still remain the same. Adding that wall will not change the temperature inside the system in any way. All right, so that's called thermal equilibrium. But now if you imagine you have the same kind of system, but now it's like on the top, it's at T1, and at bottom, that's at T2. You can imagine you have a cup of cold water, and you're pulling hot water in there. So the top and bottom will have different temperature for a short amount of time, right? But if you insert that non-adiabatic wall right away, that's going to separate these two parts, and that's going to eventually have a difference. But we haven't defined temperature yet, so that's actually not a very good example. Okay, and let's see some example problems together. I know there are lots of terminology. They're not hard. Just get familiar about it. Talk to your classmates. I don't want to say talk to your friend, because your friend will think you're mad. Talk to your classmates and try to use these terminology more often so you're familiar with it, right? Okay, so now let's imagine this, well, my little milk box again. We have some criteria of the box, and we have rigid box. And what rigid tells me is it's not movable. Likely we have no PV work that's being done for the milk inside the box, if we don't consider gravitational field. We have impermeable, so that tells you the milk cannot just spontaneously come outside from the box without anything happening. And non-adiabatic. So non-adiabatic telling you that box is thermally conducting. Okay. So now imagine some of the criteria. We have this milk just sitting there nice and easy in the refrigerator overnight. The temperature of the milk is 4 degrees Celsius, and the temperature in the fridge is also 4 degrees Celsius. So for now, let's just assume if the temperature is the same, we don't have heat transfer, or we only have infinitesimal heat transfer in between the system and the surrounding. So is that milk in the box in equilibrium with the surrounding? Right, so it is. And what about we just take it out from the refrigerator? Now the temperature inside is 4 degrees Celsius, and the room temperature is 20 degrees Celsius. So the state of that milk that we just take it out from the refrigerator, is it in equilibrium with the surrounding? No, right, because it's thermally conducting, so the temperature will change. There are heat transfer taking place. And if we put that milk outside, you can imagine that milk can go bad, but let's not worry about that milk go bad part. So now the temperatures are the same inside and outside the box. So do we have equilibrium? Right. So straightforward enough. Okay, and we have two more topics about the basic terminologies in thermodynamics. This part will act pretty much as a quick review on your physics. I know physics is one of the prerequisites, so you should be familiar with all these relationships and definitions. So mass and volume, so these are some of the very fundamental properties we use to describe any macroscopic object. And one of the things I want to use describing these things are called extensive and intensive properties. So mass and volume are your typical extensive property. So what does extensive mean? Extensive tells you it's one whose value is equal to the sum of its value for parts in the system. I know it sounds weird, right? So now imagine I have my coffee and I have my cell phone, right? So the mass of these two objects, you have mass 1, you have mass 2, and you add it up, it adds to mass total. So mass is something that you can add it up to have a total mass. Alternatively, if we're looking at density and pressure, so these are things called intensive property. So my coffee and my cell phone will for sure have different density, and you can't add these two density together and say, hey, that's a total density of your cell phone plus coffee. That doesn't work out that way. All right. Or the other way to put it is I like my milk carrot. It's, now you can imagine you have a small box of milk and a big box of milk. And obviously the mass and volume of these boxes of milk are different, but the density of the milk is the same. Right? It doesn't, the milk doesn't care whether it's in a small box or a big box. Okay. And the last concept we want to introduce is called homogeneous and heterogeneous systems. So homogeneous tells you each intensive macroscopic properties is constant throughout the system. So intensive properties, remember, that's pressure or like density. So these intensive macroscopic property is constant throughout the system. It's uniformly separated. And a homogeneous part of a system is called a phase. And in heterogeneous systems, you can have multiple phases. If that doesn't make sense to you, let's look at some example. So now imagine we have a cup of still water. Now let's assume that cup is being covered and we don't have like matter exchange with the surrounding. Now in that cup of still water, all water are in liquid phase. So is it a homogeneous system? Right, so this one is a homogeneous. Right, the density remains the same, the pressure remains the same. It just have one substance that's evenly distributed. So that's a homogeneous system. But what about a ice water? Now, that part you have to double think. It has both ice and water inside the box, inside the cup. Now your water is in liquid phase. It has its own pressure, it has its own density, and ice obviously have a different density or intensive properties. So a ice water would consider to be a heterogeneous system. And how many phases are there in this cup of ice water? 2, right? Okay, now move a little bit step further. Now we have a cup of iced soda water where you have carbon dioxide hanging around as well. So what is the nature of the system and how many phases are there? Right, so we have heterogeneous system. You have 3 different phases, gas, solid, and also solution. Okay, and I'll pause here for a little bit questions before we move on to talk about calculus. I know that's your favorite subject. Yes?
If you have something like oil on water, would you still define that as homogeneous?
So it depends, right? When you have oil in water, now you have 2 different substances of different intensive properties. As you mentioned, right, oil is on water, so the density is for sure different. So there are 2 different phases of a heterogeneous system. Now the water itself is homogeneous. That's why it's called a phase of the heterogeneous system. Yes?
Could you explain again the criteria for equilibrium where you have the...
We'll have more discussion about equilibrium. So right now it's just a quick introduction. Just, yeah, I don't think we can give you... So the thing is, I can't give you a full definition of equilibrium yet because some of the terms have not been defined. So this is going to be a prelude. Like we will be using these terms and just connect material equilibrium with like PV work and movement of the walls, thermal equilibrium with temperature change and heat transfer.
And you said removal of contacts. Is that like changing the nature of the surrounding system?
Right, so going back to our milk example, what effectively we're saying is imagine you take it out and the milk goes bad, right? during the time when milk is going back, when bacteria are doing their work, that process is non-equilibrium because you have content change within that milk box. But after, say, a long time, the reaction concluded, or when we say concluded, the reaction reached a equilibrium point. You still have new reaction taking place, but it's going to be a reversible process. And then at the end of that reaction spectrum, now it's back to material equilibrium again. Okay. All right. So the last topic of today's lecture is going to be a quick review on calculus. So we'll be reviewing both differential calculus and integration calculus. I have 15 minutes. If I don't get to finish, I may send the textbook, and it is a review, so read it. All right. So thermodynamic and 110A specifically, as you can already see in the lecture note I posted, we're going to use calculus pretty extensively. So if you already forgot about some of the rules of calculus, I highly recommend you go back and review it. Now, I'm not your math teacher, so I'm not going to give you some very complicated integral or differential equation and ask you to solve it. But rather, I hope you're not afraid of seeing like differential equations and integrals, and you're comfortable using some of the basic calculus technologies to understand these concepts. All right. As always, when we talk about calculus, you always start by definition. And also one of the common way to think about derivatives are just imagine them to be slopes of a function. Now you have y equals to yx, where y being some function of a variable x. And we'll see that linear relationship a lot in this class. We will be talking about Euler's law and Charles' law in our next lecture when we're working on ideal gases. So in here, what we have is effectively a linear relationship where P is your pressure, V is your volume, and K is a constant. Right, so we can describe P as a function of V. And same for Charles' law. You have A1 and A2 being some kind of constant, and there's a linear relationship between volume and also the temperature of an ideal gas at constant pressure and mass. You will see this kind of equation very often, like in this class. I want you to pay attention to both the front side of the equation, which is the PV equals to K, or V equals to A1 plus A2 times T. So that's the front part. The last part is also very important. So this part are the specific condition that these equations are applicable. You will see a lot of equations in this class. And if you do not pay attention to what these equations are applicable, you'll end up being saying like, I have 5 expressions of entropy, which one I should use to solve this problem? Like, try avoid that thing. Like, every time you see an equation, try to look at it and think about a scenario that's related to that specific equation. Okay. Yeah, and a little bit more about calculus. So if we're talking about a function, sine x over x, and you can imagine what that means. It's like we have the limit of this function, sine x over x, equal to 1 when x is approaching 0. So it's just some review on calculus. And also you have how do you define the slope? You have like y1, y2, x1, x2. And your slope is obviously defined as y2 minus y1 over x2 minus x1. And when you take that difference, or delta y and delta x, if you take that difference to infinitesimal movements only, and then you have your derivative of that function. Okay, and well, a bit more about derivatives basically tells you about the instantaneous rate of change of any function you are interested. There are two different ways we write derivatives. You can have the y prime notation. Basically, it's the same idea, right? dy over dx, telling you we're taking the derivative of x for a function y, which is a function of x. And when working on derivative, there is some of the rules that can be helpful. Like, for example, you have the chain rule. So that part is if you are taking the derivative of some new function r, of some function r, well, so z is a function of r, and you don't know how to directly get the derivative of dz over dr. So you can define a new function and link it together using the chain rule. So for example, in here, like we don't know how to directly take derivative of sine 3r squared, but we can define in here, we have z equals to sine 3r squared, right? So we'll have x equals to 3r squared, and then z equals to sine x. And both of these derivatives are easy to solve. And obviously, you can solve the derivative of sine 3r squared by using the chain rule. So try it out. I mean, you can find the answer and the walkthrough in our annotated notes. And here are some of the common formulas for differentials. These are just like really, really basic functionals for differential equations. I don't really expect you to remember it, but if you use it like 5 times, 10 times, eventually you'll get it. Okay. And one of the things we will be using a lot are partial derivatives. So in thermodynamics, normally we're dealing with multiple variables contributing to something observable. So a function can have 2 or more variables, and obviously I have a typo here. Sorry. So effectively, what we're talking about here is that's the partial derivative of z. So we're just keeping one of the variable constant and taking the partial derivative of the second variable. I left some practice problem here for you to try it out. For example, can you find the 2 partial derivatives of this function z, which is a function of x and y? So you can try it out, how to find the partial derivative of z with respect to x at constant y, and also how to find the partial derivative of z with respect to y at constant x. Actually, we have some time, so we can just quickly work on it. If we're just keeping y being constant, so in the first one, when we're working on it, the y just acting as a constant, we just put it down. So y third, and we take the derivative of x. And the same on the right-hand side, we keep y being constant. And we take the derivative of x. All right, just keeping that variable constant but when you're doing the partial derivative. It doesn't necessarily mean that that variable is constant throughout the entire process. It's just when we're taking the partial derivative, we treat it as a constant. And same here for the right-hand side. If we're considering it, taking the partial derivative of z with respect to y, keeping x constant. So the x keeps constant, 3y squared, and also x exponential by x. All right, so these are just, I mean, the example I'm giving you here are the example or the level of difficulty our calculus will be. So it's not going to be something like really, really hard, but you need to get familiar with using the calculus throughout our course. And there are some more information about partial derivatives. So for example, you can write out the total differential of a function with multiple variables by using partial derivatives and also derivatives. And that's by definition, dz equals the partial derivative of z over x at constant y times dx plus partial derivative of z over y at constant x times dy. It's long, but hopefully it's not too hard to capture. There are also some of the very important equations we will be using, especially when we start talking about Gibbs equations. But again, these are the things, like just have it handy. Like don't if you don't remember it, it's fine, but have it handy and know when and where to use them. So for example, the first rule here is say, if we're keeping y being constant, we can keep x as constant as well. So the partial derivative of z over x at constant y equals to 1 over partial derivative of x over over z at constant y. So you can flip these two. Okay, that's the first rule. Second rule is again it's the relationship between different partial derivatives. Again, it's a relationship between x, y, and z. Now imagine x is a function of y and z. Y is a function of x and z, and z is a function of x and y. Now we have this chain rule telling you that if you take it like partial derivative of x over y at constant z, and then partial derivative of y over z at constant x, and partial derivative of z over x at constant y, that equals to -1. All right. I feel like I should be a rock star somehow. It's just like calculus rock. Anyway. And then the last one is a similar one we saw before with the actual differential equation. The same rule applies for our partial derivatives as well. And I think I have some mistakes here. This should be an x. Yeah. So you can use a hypothetical equation to help you to solve a partial derivative. Okay, and that's the end of our quick review on differential equations. I know I went really, really fast. That feels like 2 months of calculus in 10 minutes. But nevertheless, that's what we will be using. I mean, again, I don't expect you to solve really, really complicated differential equations. That's not our goal here. The goal here is to refresh your memory on calculus and use it and not to be afraid of it. Okay. I have 2 more minutes. I'm just going to quickly mention integral calculus. You will have a more detailed review in your book chapter. So for integral calculus, the idea here is now we know how things are changing. How do we find out the volume not the volume, the area that's under a specific curve? You take integrals of those infinitesimal steps you divide it to when you're doing the derivatives. Now you have 2 different types of integral. You have the definite integral, where basically in that definite integral, you know where that start and where that end. So it starts from A, ends at B. You can also have indefinite integral. So these are just some of the indefinite integrals that you can work on. So basically, it's just give you a general formula of after taking that integral, what we're getting. Okay, and see if we have just a quick minute to do one example together about integral. So in this case, remember, we can similarly apply the chain rule. So that's rough. So let's define z equals to x squared. And then what we have is dz, equals to 2x dx. That's taking the derivative of z over x. Now this equation then becomes 3 x times e to the x squared dx will give you because we know that dx and dz has this relationship, we will end up having to be 1/2. And now we have z equals to x squared, so these will change from 4 to 9, e to the z dz. All right, and you can solve this integral to give you an actual number. Just a quick review. I mean, you have plenty of practice on your textbook you can try out. Okay, and that's all from today. I hope I didn't scare anybody away by calculus. That's not my fault. But nevertheless, have fun, and I'll see you next Monday.